This is Quantitative Methods, and this is the reading on statistical concepts and market returns. Now, before I get into the slide deck, I want to kind of give you a general philosophy about statistics. I've been teaching for a long time, and students regularly complain about learning statistics. I was the same way when I was in college. But when I got to graduate school, I learned that statistics is really quite useful. And the quantitative methods reading here really is awesome. So my charge to you guys is for you to think of statistics as your friend, not your enemy. Let's embrace these statistical concepts. All right, lots of LOSs in this reading. First one is to distinguish between descriptive statistics and inferential statistics, between a population and a sample, and among types of measurement scales. So what is statistics, first of all? Statistics is concepts and rules and procedures that help us interpret data. I mean, that's really what we're trying to do. We collect data, and then we ask ourselves the question, what do we do with this data? We can look at it, we can see highs and lows, and we can see somewhere in the middle. But there are many more things that we can do regarding that data. And so statistics is really going to allow us to interpret that data and make some informed decisions and some predictions regarding the data and the implications for future decision making. Data are just simply facts or observations that result from an investigation. Two branches here: descriptive statistics, which are summarizations regarding the data. And it's fairly well known that there are 4 measures that describe any kind of a sample: the mean, the variance, the kurtosis, and the skewness, each of which is discussed in a later LOS. Inferential statistics, on the other hand, suggests that we can draw some valid conclusions concerning an entire population based on what we collect from a sample. And this involves things like probability distributions, hypothesis testing, probability distributions. That's for a later reading. Distinguish between populations and sample. A population is a summation of all elements. In other words, it's the totality of observations. For example, the total number of CFA candidates in a given year, or the total number of people in a country, or the total number of people living in my house. A sample, on the other hand, is part of that population, and a sample should represent all of the elements of the population as a whole. And so the idea is that we look at a sample and we can make conclusions about the entire population. I mean, for example, if we want to know what the average level 1 CFA candidate looks like in terms of hours studying on each reading or each study session or a particular topic, we don't really need to spend the resources and the time and the energy going out and collecting data on each of those individual ones. I mean, how many people take the CFA exam every year? Is it well over 100,000? We don't have time to figure out how to contact those 100,000, let alone perhaps the resources to record the data and collect the data. So what we do is we take a representative sample, and then we can make reasonable conclusions about the population. How about distinguish between and among types of measurement scales? Several different types of measurement scales. Nominal scales, these are used to label variables but really have no numerical meaning. Like, for example, we could say that 1 represents males, 2 represents females, or we could say 33 represents males and 34 represents females. The number really doesn't mean anything. It's just that we're distinguishing between 2 groups. Ordinal scales are probably what we're used to during our whole life. They're used to represent ordered categories. And so it's the order of the categories that are important, but not the differences between them. which cannot be quantified. And so someone asks us how we're doing, and we might say, you know what, we're doing great today. Or someone might say, how you're doing, and another day we might say, we're not doing very well today. And so on a scale, we could say, 1 is I feel terrible, 2 is I feel okay, 3 is I feel pretty well, 4 I feel great, 5 I feel super de-duper, or whatever it is. So what do I have in the bullet point there? 1 is poor, 2 is good, 3 is excellent. So it's kind of a way to quantify sets of behavior or how you feel. Interval scales, on the other hand, just measure the difference between intervals. So here's an example here. If we've got a couple of different financial professionals, and each makes an average salary of $63,000 and $72,000 and $101,000. The portfolio manager earns about $30,000 more than the investment analysts and $38,000 more than financial analysts. So that's an interval scale. Ratio scales have all the properties of interval data, and the ratio of two values is meaningful. Variables such as distance and height. For example, you might say, it's 5 miles from my house to my work. And so we start with 0. And so this is the scale that starts with 0. Anything that starts with 0 and then moves like height, your 0 height. You're not really 0 height when you're born, but you could be 0 height. But then if you're 6 feet when you're 18 years old, that has meaning. How about the difference between a parameter and a sample statistic? A parameter refers to a measurement that's used to describe the entire population. And there is a population mean and a population standard deviation, as opposed to a sample statistic, which is a statistic that describes a sample. And so you can have an average sample and an average sample standard deviation. A frequency distribution refers to the presentation of a statistical data set in tabular format, just to make sure it's simple. Let's talk a little bit more about a frequency distribution. So here's a sample. We've interviewed 30 CFA level 1 candidates and asked them how many hours have they studied for quantitative methods. Oh boy, look at those numbers there. What does the Institute recommend? 350 hours of study. So look at some of these guys. 124 hours. Wow, that's good. Let's make a frequency distribution table with 5 classes. Minimum is 67, maximum is 125. All right, so how do we go about constructing a frequency distribution based on, what is that? We've got 30 candidates, so we have 30 different hours studied. All right, so 5 classes is going to be appropriate. Let's determine the class width. And that's a relatively simple formula. Just take the maximum, subtract the minimum, divide by the number of classes, and you're around there. So the class width is around 12. So then we determine that the class limits. So we're starting with 67, and then going up to 78. So 67 to 78 is one class. And then the next number is 79. Up to 90, that's another class, and then 91 to 102, etc., etc. Mark a tally for each one to get the frequency. So we have 3 in the first class, 5 in the second, 8, 9, and 5 in the subsequent classes. That gets our total up to 30. Let's distinguish between relative and cumulative relative frequencies. Let me give you just a quick definition here, and then I'll show you an example in the next slide, and it'll make it obvious. Relative frequency is simply the percentage of observations falling within the class. It's kind of like an interpretation of popularity of certain classes. Cumulative absolute frequency is just the sum of those frequencies. So back to our example, let's put together this table. There are our class limits. 67 to 78. So there's our tally, and there's our absolute frequency. So there's the 3, 5, 8, 9, and 5 that we had before. Of course, they sum to the 30 CFA level 1 candidates that we interviewed. And then the relative frequency is just going to be each class's absolute frequency over the total. So 3 out of 30 is 10%. 5 out of 30 is almost 17%, and so on. And notice those relative frequencies, then they must sum to 100% because you have 30 out of 30, and that has to be 100%. And then we just do some summing in the next column. We call that the cumulative absolute frequency. So our first class had 3 in it, then our next class had 5 in it. So 3 plus 5 is 8, right? And then 8 plus 8 is 16, and so on, all the way down. And then the cumulative relative frequencies then are going to be the addition of those relative frequencies. So you take the 10 and you add the 16.67, that gets us up to 26.67. Add the 26.67, and you get 53.34, and so on, all the way up to 100%. So this is a good table to address this LOS, to give you an idea of the relative, the cumulative relative frequencies, and then the distribution. What about pictures of the data set? We're going to call those histograms and a frequency polygram. And so a histogram just shows the distribution of numerical data in the form of a chart. So look down on the bottom right of the slide, and on the horizontal axis I have the class intervals, and then the frequency of those intervals on the vertical axis. And so there's the 3, the 5, the 8, the 9, and the 5. So that is a histogram. A frequency polygram is similar to the histogram, but unlike, here, let me go back here, unlike the horizontal axis where I have the class intervals, in a frequency polygram I'm going to have the actual data sets. And so I'm going to call those the midpoints of each data set, and we can calculate the midpoint of each class interval relatively simply. Take the lower limit and then take the average of the upper and the lower limit. I'm sorry, not the average. Take the difference between the upper and the lower limit and divide by 2. And so if you picture, let me go back here, you picture the histogram. So that's upward sloping and then it's downward sloping, right? Indicating that there's more data points in the middle. And then the polygon is upward sloping and then it's downward sloping, which indicates kind of the same thing. All right, how about some measures of central tendency? All right, let me give you a definition of central tendency. This is a fancy term for, in the statistics world, to describe what happens in the middle of the distribution, points of central tendency. We can do population mean, sample mean, arithmetic mean, weighted average, geometrics, harmonic, median, mode. We can do all that stuff. So I have an example where we're going to compute all of those things. But these are all points of central tendency. All right, mean, median, and mode. You probably remember that from some undergraduate class. All right, population mean and the sample mean. Population mean is just exactly what it suggests. It's the mean of all of the population data points. And so you can compute that by summing all of the data points in the population and dividing by n. You do the same thing with the sample. You add all of the sample points together and divide by n. Now notice in the formula that we divide by an uppercase n with the population. That's to signal that it's the population, and we divide by a lowercase n in the sample. That's to indicate that it's the sample mean. Big N and little n means population and sample. Both of these are arithmetic means, which means that as financial analysts, we can use that arithmetic mean to try to predict future performance. And so the reading uses that term, forward-looking context. It's not always perfectly accurate, of course. But that's why we need to compute things like standard deviation to see really how accurate that mean estimate can be. All right, a weighted mean is simply going to take into account the weight of every observation. You know, for example, if we have a bunch of points between 1 and 100, and we have a lot of them in between 1 and 10, and only a few of them between 90 and 100, we need to weight those a little bit more that occur early on in the sequence than later on in the sequence. The geometric mean only works for non-negative values. And what we're going to do with the geometric, here, let me go back here. When we do the population mean, what we do is we add the data points together. For the geometric mean, we're going to multiply the data points together. And then, now watch this, instead of dividing by n, we are going to raise the sum of all those products to the 1 over n. Geometric mean is an excellent measure of past performance. The harmonic mean is another point somewhere in the middle that de-emphasizes a data set when there are significant outliers. And so it really focuses on average growth rates within the data set. And so the important thing about the harmonic mean is that it reduces the impact of outliers. I mean, for example, if you had a data set like 4 and 5 and 6 and 7 and then you had 39 in that data set. Well, going back here, calculating all of these other means, that 39 is going to have a dramatic impact on the resulting statistic. But the harmonic mean kind of it reduces that. The median is, of course, the statistic in the very middle. If there are an odd number of data points, then you just take the middle value. If there are an even number of data points, then you have to take the average of the two middle values. And then the mode is the most frequently occurring data point. All right, so here's an example. Simple example. We've got a company that generated the following rates of return over 6 years. So we got 2%, 2%, 4, 6, 8, and 12%. So first of all, looking at that, you're going to look at that and say, okay, 2 and 4, you can kind of visualize this and say, all right, the mean is probably going to be a little bit less than 6%, somewhere in there when we calculate it. So let's go ahead and do the calculations. And I'll let you guys pause the video to make sure that you can calculate these things. But just a few points of interest here. Notice the arithmetic mean, we're just adding and then dividing. And then the weighted mean, we're weighting each one by its number of occurrences, so that gets us to the same number as the arithmetic mean. Geometric mean, we're adding 1 to the decimal form of the interest rate, 1.02, 1.02, 1.04, multiplying all those together. And then instead of dividing, we're going to raise it to the 1/6 power. And then for the harmonic mean, there's the formula. We take the n, 6 in the numerator, and divide by the summation of 1 over each variable in its, data point in its percent form. And then the median, since there are, what is that? There's an even number, right? There's 6, so you got to take the average of 4 and 6. And then the mode is 2%. So go ahead and pause the video, and I will continue. How about quartiles, quintiles, deciles, and percentiles? All we're doing here is dividing the data into parts that are easily recognizable. So quartiles are divided into 4 parts, quintiles, 5 parts, deciles, 10 parts, percentiles, 100 parts. I always ask my children every day, how are they feeling? What's your percentile? And usually I get like, oh, I'm 42 percentile today, Dad. Or some days they're 73 percentile. All right, how about a range? This will be relatively easy. And then the mean absolute deviation as well. Then we'll have to spend a little time on variance and standard deviation. So the range is simply the difference between the max value and the minimum value. We did that a few slides ago. The mean absolute deviation is going to be exactly what that term suggests. It's a deviation. So notice in the formula we're going to take each value minus the mean value, and we're going to add those, and then we're going to divide by n. So it's kind of like an average error. An average error. So think about back in those 30 level 1 CFA candidates. We're going to take each one of those numbers. They were like, 67 and 81 and 103 and 122 and 124. Take each one of those, subtract it from the mean, add those together and divide by 30, and that's going to give us the mean absolute deviation. All right, here's where students typically lose interest and lose focus and lose concentration when describing statistics, when we talk about variances and standard deviation. So first of all, the standard deviation is just the square root of the variance. So both of those terms are measures of variability. To compute a variance, what we're going to do is, are you ready for this? We're going to do the exact same thing that we did back here for the mean absolute deviation. We're going to take each observation and subtract it from the mean, but in the variance, both in the population and the sample, we're going to square that deviation. And then we're going to sum them, and for the population variance, we divide by n, and for the sample variance, we divide by n minus 1, which is also known as degrees of freedom. Now, a couple of things here. Notice that since we're squaring a number, the variance will always be positive, which means the population variance will always be positive, and the sample variance will also always be positive. But the reason that we square it is, of course, to get rid of the negative, but the example that I always give my students is the following. Picture me standing in a room, and picture me taking 4 steps straight in a straight line. And as I take these 4 steps, you can count along with me. I go 1, 2, 3, 4, and you know and I know that I've taken 4 steps. But suppose that I say, all right, count the number of steps now, and I take 2 steps in a straight line, then I turn around and take 2 steps back to where I started. And I say, how many steps did I take? And if you weren't paying attention, you might say, hey, you didn't take any steps. You started where you ended. Well, that's why we square this thing, to count the true number of steps, to get rid of the steps forward versus the step backwards. So clearly I took 4 steps when I took 4 steps forward, and clearly I took 4 steps when I took 2 steps forward and 2 steps backward, but it might appear in the second case that I didn't go anywhere. So to eliminate the didn't go anywhere part, we square it. And so that's the population and the sample variance. And then we just take the square root to get the population standard deviation and the sample standard deviation. Let's talk about this dude, Chebyshev. Chebyshev is considered to be, among others, the father of mathematics in Russia. He lived in Russia in the 1800s and was extremely well known in Moscow. He taught at the University of Moscow and then globally during the end of his life. And what Chebyshev was interested in doing was trying to figure out how far away from the mean can we get depending on the standard deviation of a sample or the population. So if I go back here to the population variance or the sample variance, what I'm actually measuring is a degree of error. I have the mean, say the mean is 10%, and I have the standard deviation, say the standard deviation is 3%. Well, I want to know how wrong I could be if I think the next observation is going to be 10%. So a larger standard deviation means that I'm going to have a greater error of a greater degree of error, a greater mistake. How about this as it applies to financial analysis? I'm going to have greater risk. So back here, what Chebyshev was interested in is if I have a mean and a standard deviation, how confident can I be that the observations are going to fall within a certain range? And so Chebyshev's theorem states that, I'm going to read this, for any set of observations, sample or population, and regardless of the shape of the distribution, that's important, the percentage of observations that lie within k standard deviations of the mean is at least 1 minus the reciprocal of k squared. All right, so there's Chebyshev's inequality formula, and there's an example there at the bottom. If we want to do 2.8 standard deviations, we get an 87% percentage of observations that lie within 2.8 standard deviations. So that gives us some information about the data set. We have an 87% chance of falling within about 3 standard deviations. All right, how about coefficient of variation? Coefficient of variation is really just a ratio of what we've been talking about. We put the standard deviation in the numerator, and we put the mean in the denominator. And so these are different for the sample and for the population. But what they do is they give us a measure of the amount of variability in the data set relative to its mean. Let's do a quick calculation with a sample of, what are those 5 numbers there? All right, so for the sample there, let's work out the mean. So we add those numbers, divide by 5, that gets us 40. Work out the standard deviation. So notice what we're doing. We're taking 40 minus 40 squared. So 40 is that first observation minus the mean. We square that, so that number goes to 0. And then we continue to do this. 46 minus 40 squared plus 34 minus 40 squared, etc. And so we get a standard deviation of about 5.5. So we put that in the numerator, we divide by the mean, so we get a coefficient of variation of 13.8%. What this does is it measures risk per unit of return. All right, so notice in the numerator we have this standard deviation, which I told you is a measure of risk, divided by a mean. And so if we're dealing with a series of stock returns or bond returns, then it should be obvious that we're going to do it's a measure of risk per unit of return. Another example, mean monthly return on a mutual fund of 0.5%, standard deviation of a little bit more than that. Compare that with another mutual fund that has 1.5% mean monthly return and a much larger standard deviation. Okay, what can we conclude about these two investments? Well, first off, the Y has a much greater standard deviation. So just based on that, we're going to say, boy, that has more risk. But let's compute the coefficient of variation to verify that. And of course, we have 1.16 versus 4. So Y is much riskier than X. All right, final LOSs here. Tell us about skewness and kurtosis. So this one says to explain skewness. Now remember, back in the very beginning, we talked about the mean and the standard deviation. Those are the first 2 moments of a distribution. Skewness is the 3rd moment of the distribution. So look at the bottom of the slide. I have a bell-shaped curve. I'm calling this symmetric. So the left side is kind of the mirror image of the right side. But not all distributions are symmetric and follow a bell-shaped curve. Some have positive skewness, which is the middle graph, and some have negative skewness, which is the far right graph. Now, it's a good thing the LOS doesn't say to compute the measure of sample skewness, because you'd have to use that formula there. But it asks you to explain it. So look at this. This is going to be really interesting. Notice that formula, forget the first part with the n's and the n minus 1s. Look at the second part. We're still taking each observation, each x value, and we're subtracting it from the mean, but instead of squaring it to get the standard deviation, we're raising it to the 3rd power to get the 3rd moment of the distribution, which is skewness. And so if skewness is positive, then we say the distribution is positively skewed. Let me go back and show you that picture down there in the bottom middle. And if SK is negative, then it is it is negatively skewed. Whoops, I went the wrong way. And there's the picture on the bottom right. Okay, so explaining skewness really is just a matter of saying it's kind of like the next step. It's the next step after computing standard deviation, and it tells us whether the distribution leans to the left or it leans to the right. Kurtosis then is the fourth moment of the distribution, and kurtosis reflects a difference in the normal distribution here on the bottom left of a higher peak or a lower peak. And so let's go ahead to the formula here. Oh my gosh, you should have been able to predict this. Look, if the third moment means we're going to raise it to the third power, then the fourth moment means we're going to raise it to the fourth power. And that's all we're doing to calculate kurtosis. And so explain this as like the step after skewness, in which we can be leptokurtotic or platykurtonic, and that all depends on whether k minus 3 is either greater than or less than 0. And there we go. Statistic concepts, your friends. Next up, probability concepts.